Hello friend, in today's lectures we are going to discuss about the slope and deflection of the beam, and also we will discuss about elastic curve, deflection of the beam, and what is meant by slope and the relationship between the slope, deflection and radius of curvature of the beam. Now let's see here, the cantilever beam is subjected to point load. When the point load is acting on that beam, the beam is deflects from its original positions in the y directions, and in that side it is observed that when the beam or cantilever is subjected to some type of loading, it deflects from its original positions. The amount of this deflection depends on its cross section and bending moment. Now, when we design the beam is designed on the basis of strength and stiffness. So, when we consider the strength at that time, or when we design the beam on the basis of strength criteria, the beam should be sufficiently strong to resist the shear force as well as bending moment. It means, in other words, we can say that the beam should be able to resist the shear stresses and bending stresses. That is one thing. But when we consider the beam as a stiffness as a criteria, at that time the stiffness means stiffness is equal to load per unit deflections. In that side, W is the applied load on the beam and delta is the deflections when the load is acting on that beams. So beam should be sufficiently strong to resist these deflections. In other way, we may say that the beam should be stiff enough not to deflect more than this permissible limit. If we say here the beam is deflected from that side, when we consider the cantilever beam, if we consider simply supported beam, the beam is deflected from these original positions by a distance y, or deflections we may denote by y, or you may denote by delta also. So y and delta are the notations for the deflections in that side, and this deflection curve, or it is known as the elastic curve. When neutral axis deflected from its positions, then this known as elastic curve. And if we take a tangent to that elastic curve in this manner, or here if we say this side, so these tangents having some angles, and that angles, that is denoted by theta, or sometimes it is denoted by I. It is denoted by I or theta. In that side, I or theta, which is known as the slope. So here there are three definitions or three terminology for this. First terminology is elastic curve. Second terminology, deflection of the beam. And third is the slope. Now first we will see what is meant by elastic curve. Elastic curve is defined as the deflected axis, or here we may say deflected axis of the beam is known as the elastic curve. Here we are showing this in this manner, here we are showing this dotted side, which bends into the arc of circle having some radius r, that is called, we may say, radius of curvature. and this elastic curve is very flat and slope at any point is very small, and this slope of the points is denoted by tan theta is equal to dy by dx. Now second point is deflection of the beam. The deflection of beam at any point is defined as the vertical distance between the axis of the beam before and after the loading. In that case we have shown here y, or here you may say delta also. Here also this initial axis, when the load is acting, then that beam deflected from its original position. So this distance y or delta, then that is known as the deflection at that point. It is denoted by delta. And deflection at the support means this side, or you may say this side or this side. Deflection at this support is always 0. Deflections at the support is always 0. These points, at this point you may say deflection 0, here deflections will be 0 always. And third term is slope. The slope is defined as the angle in radian between the tangent and the elastic curve. This side you are saying, if we consider this simply supported beam, this angle is theta or I, which is known as the slope, Now let's see the relationship between slope, deflection and radius of curvature. In this case, figure shows the curvature of the beam, and here we consider the sections PQ, the small element of that. ds is the length of the beam, r is the radius of curvature, c is the center of arc, psi is the angle which the tangent at P makes with the x axis, whereas psi plus d psi angle which tangent at Q makes with the x axis. Now consider this angle PCQ. Angle PCQ is equal to d psi. Now the length of these sectors PQ is equal to, according to our equation, S is equal to r theta, whereas S is the length of that PQ, here ds is the length of that. So according to this we can write here ds is equal to r into d psi. Therefore r is equal to ds upon d psi. In that case ds is very small, so you may write here ds is equal to dx. So r is equal to, you may write this equation, dx upon d psi. So here I am rearranging that equations. 1 upon r is equal to d psi upon dx. Now if x and y are the coordinate at point P, then we can write here tan psi is equal to dy upon dx. But psi is very small, so you may write here tan psi is equal to psi is very small. So psi is equal to dy by dx. Differentiate this equation with respect to x. So here we may write d psi upon dx is equal to d square by y upon dx square. But 1 upon r is equal to d psi upon dx. So we may rearrange that equations. 1 upon r is equal to d square y upon dx square. We may say this equation number 1. Now, according to our Flexural equation, m upon I is equal to E upon R. So therefore, bending moment m is equal to, we may write E into I upon R, whereas m is called as the m is equal to bending moment if we put the value of here r, put 1 upon r is equal to d square of by y upon dx square. So that equation become m is equal to ei into d square y upon dx square. This is the equations for bending moment. Now in that case, if we differentiate these equations with respect to x, differentiate with respect to x, then that becomes dm upon dx is equal to ei into, it becomes d cube y upon dx cube. But dm upon dx is equal to shear force, is equal to shear force. So we may say that shear force F is equal to ei into d cube y upon dx cube. Again we will differentiate this equation with respect to x, differentiate again with respect to x, so that becomes df upon dx is equal to ei remains constant, so that becomes d raised to 4 y upon dx raised to 4. But df upon dx is equal to w, that is rate of loading, that is rate of loading. So rate of loading w is equal to ei into d raised to 4y upon dx raised to 4. So from that above equations we can see the relationship between slope and deflection. So in that case, deflections is equal to y, slope is equal to dy by dx, bending moment is equal to ei into d square y upon dx square, shear force F is equal to ei d cube y upon dx cube, and rate of loading last w is equal to, you may write ei into d raised to 4y upon dx raised to 4. This is the equations for elastic curve and relationship between curvature, slope and deflections.